So in a previous video, we spoke about something called the atomic number, and that was how many protons are contained within an atom of a given element. So for example, if I had some hydrogen, I have an atomic number of 1, which means hydrogen atoms have 1 proton in them. However, in chemistry, that is not the only number that we have to think about when we're talking about elements. So the second number we're going to look at in this video is the mass number. So here is, to start us off, an atom, or a diagram representing an atom, and it contains the 3 subatomic particles that we spoke about before. So in the middle we have protons and neutrons, red and green, and orbiting around the outside I've got little blue dots to represent my electrons. Now just to point out, in the middle I have drawn all the little red protons on the left and all the little green neutrons on the right. That's not very realistic. In reality, the neutrons would be in between all the protons, holding them together like glue. Because if they weren't there, if those neutral neutrons weren't there, then all the positive protons would just repel away from each other. So they would all be kind of meshed together. But I'm going to use this diagram in a minute, and I've drawn them like that for a specific reason. But just remember, in reality, that's not how it would look. And then orbiting around the outside are the electrons, which in this video are going to basically be ignored for a reason I'll discuss in a little second. So this mass number then is the number of protons plus the number of neutrons. So when you're thinking about the mass of an atom, the mass of a sample of an element, the only subatomic particles that are contributing to that mass are the ones that are in the middle, in the nucleus of the atom. Now, why is that? Why don't the electrons matter then? Because surely they count as part of the atom. Well, they do. They are definitely part of the atom, and they are very, very important when it comes to lots of reactions in chemistry and how the element will behave. However, the electrons that orbit this nucleus are so tiny and so light that they don't affect the overall mass of the atom. Now, all the subatomic particles are tiny, but the electrons are particularly tiny. Compared to the protons and the neutrons, they are very, very small and very light. So when we're thinking about mass, the electrons just basically don't count. It's just the stuff in the middle, which is the protons and the neutrons. And you can count every individual proton as a mass of 1, and every individual neutron, again, as a mass of 1. So it's just a case of adding them all together. That's the total mass for that atom, if you like. Now, at this point, we have got elements, we have got element symbols to represent those elements, we've got an atomic number, and now we've just added in a mass number. So that's lots of information. So to represent all that information in one nice neat package, chemists use something called Nuclide Notation. So what does that mean? Well, it's basically just a nice, tidy, neat way for chemists to represent information about any given element. So there's 3 important facts, or 3 pieces of information that you need to include when you're drawing nuclide notation. So first of all, nice and large in the middle, you have to have the element symbol. Okay, so that's just whatever the element is. So for example, hydrogen would be a big capital H. Down at the bottom left-hand corner is the atomic number. Remember, that was the number of protons in the nucleus of an atom. So sticking with my hydrogen example, I would have a big capital H, and then a little number 1 down the bottom left corner, which means 1 proton. And then finally, at the top left, I would have the mass number, and that's the one we've just learned about. So that would be the number of protons plus the number of neutrons. So for hydrogen, in hydrogen's case, that's actually also a 1, but I'm going to get on to how to work that out, or how to use that to work something else out in a second. So just to see what that looks like for an example then, if I took chlorine, I should have capital C, lowercase l for the symbol, nice and big in the middle. I would look up my periodic table and find that it's 17th in the list, or know that it has 17 protons, and put my atomic number down the bottom left, which is 17. And then up the top, again I can look this up in the data book, 35 for the mass number. So that's something that you can look up. That's a value. You're not expected to know these values. These are things that you can look up and find out. What you are expected to be able to do at National 5 level, however, is use these numbers to give key pieces of information about this atom of chlorine. So, for example, how many protons are contained in this atom of chlorine? Well, that's an easy one because you can just look straight at the atomic number, and that's exactly what the atomic number tells you. If the atomic number is 17, this atom has 17 protons, because that is what that information is all about in the first place. What about then the number of electrons? Well, if it's an atom, it should be neutral. It should have no charge. It should be neutrally charged. And if it's neutral, if it has no charge, that means it must have the same amount of positive protons as it does negative electrons. So the number of electrons must be 17 as well, because these have to cancel each other out. These have to balance. They have to be the same if this is an atom, which it is. So if it's got 17 protons, it must have 17 electrons to cancel out that charge. But what about number of neutrons? This is slightly different. You have to do a little quick sum to figure this out, quick calculation. So I have the atomic number, which tells me the number of protons. That's not really helpful here on its own. I have the mass number, which tells me, well, let's remind ourselves, the mass is the number of protons plus the number of neutrons. So using those two numbers, I should be able to figure this out. So the way that I do that is just take the total mass, or just the mass number, basically, and from that, take away the atomic number. And then it should be dead easy. So in this case, it's just 35. That's the total mass. That's all the protons, all the neutrons. Take away 17. Because that's the number of protons that I have. I'm only interested in the neutrons. This total tells me about both. So I need to get rid of those protons. And then the answer to that is 18. So I have 18 neutrons. And the way to think about that, just going back to my diagram quickly, is if all the mass is in the middle, I'm only interested in the number of neutrons. So I need to take away the number of protons. And that will leave me with just the neutrons. So it's mass number, take away atomic number, equals number of neutrons. So just to recap then, mass number is number of protons plus number of neutrons. That tells me the overall mass of the atom, remembering that the electrons don't contribute to that because they're so tiny and light. And then to represent the mass number, the atomic number, and the element symbol, we use something called Nuclide Notation. And that's really handy and a quick way to figure out number of protons, number of electrons, and through a quick sum, the number of neutrons.